All right. Hello, everyone. It's Kalen Langley in ECE275 Digital Design. This is lab number 7. Uh, for this lab, we're tasked with creating a counter which counts the following sequence 010, 110, 000, and 011. You're to utilize JK flip-flops with the synchronous active low clear in and preset in, and then to simulate the design on model sim and verify its correctness. Below you can see the diagram of the counter circuit. So this little bubble indicates that the reset is an active low. So whenever reset is high, it will start counting through the sequence. And you have 3 bits for the output of Q. So next, I created the paper design. It started off just with uh, drawing out the counting sequence, the 010, 110, 000, and 011. After that point, it resets back to 010, and at any point in this sequence, if the reset's triggered, which would be active low, it reverts back to the original starting point to 010. Yep, just double check how it was active low. 1 second. Okay. So in order to create this logic, we're going to need 3 JK flip-flops, and we'll designate those by QC, QB, QA, and the next state QC, QB plus, and then QA plus. Then you have JC, KC, JB, KB, JA, KA. In order to create this, you need to draw out the truth table for the JK flip-flop, as you can see here. First 2 bits are the hold, the next 2 are the reset, next 2 are the set, and finally the last 2 are the toggle. Once we have this, we can create the Q and next state Q for J and K. So whenever Q are both zeros, J and K will be 0 and X, or don't care. And whenever Q and Q plus are 0 and 1, you have J as 1, K as X. Q1, Q plus 0, J is X, K is 1. And then Q and Q plus, you have X for J or don't care, and 0 for K. So referencing our counter sequence, 0, 0, 0 is in there. So the next state would be 0, 1, 1. 0, 0, 1 is not in this sequence, so you have don't cares. 0, 1, 0, which would be the first step in the sequence, would proceed to 1, 1, 0. You have 0, 1, 1, which would revert back to the first again. So you have 0, 1, 0. 1, 0, 0 is not in there. You have don't cares. 101, again, don't cares. You have 1, 1, 0 that goes to 0, 0, 0. And finally, 1, 1, 1 is not in the sequence, so don't cares again. All right, now using this table here, we can compute what the JC, KC down to JA, KA will be, and I'll walk you through that step now. So whenever J or QC, QC plus or zeros, you have 0 and X for JC, KC. QB, QB plus or 0 and 1, you have 1 and X. QA, QA plus or 0 and 1, and you have 1X. Don't care for this wrong. 0 and 1. You have 1X, 1, 1, X 0, 0, 0, 0X. And we got 0, 0 again, as you can see here. So it's 0X, 1, 1, X 0, 1, 0, X 1. For this rung, we have don't cares again for this rung here. Now we have 1, 0, should be X1, 1, 0 again, you have x1 again, and 0, 0, 0x, and finally for the last row, you have don't cares. Now I created K-maps for the equations. Using this table here, or the column, and transpose those over into the individual components and got the equation, or the simplified equation for each output. Took that and used it to create the logic diagram. Since it is synchronous, we connected all the clocks to the same signal. For the reset, in order to create this logic for JK flip-flop C, it goes to the clear in. And for JK flip-flop B, it goes to the pre-in. And finally, for JK flip-flop A, it goes to the clear in. We assigned 1 to the pre-in on JK flip-flop C, 1 to the input of clear in for JK flip-flop B, and then 1 to the pre-in of JK flip-flop A. Now we move over to Quartus, and we're going to use structural VDHL programming in order to create this counter. So this is our main counter block. And as we scroll down here, you can see whenever we call these counters, oh, this is a test bench. We create that in model sim. Okay, here. Yeah, so here we start off, we call the components, and then we created those JK flip-flops in its own little program that we use to call it. And this test bench, I'm just opening it from Quartus, but like I said, we do create it in model sim. Now we're going to move over to the model sim and verify its correctness. So here's the snippet that I used to submit the assignment. So with our reset low, we're not counting due to that not. So it's going to reset back to 0, 1, 0. Whenever it's high, it will start counting. So it goes from 0, 1, 0 to 1, 1, 0. And from 1, 1, 0, we go to 0, 0, 0. From 0, 0, 0, you go to 0, 1, 1. And so forth, and that repeats itself indefinitely until the reset is triggered. So we'll step it through again, and now resetting back to the first instance, 0, 1, 0, then to 1, 1, 0, 0, 0, 0, and 0, 1, 1. We'll scroll back. I started here because it was a nice little snippet to make sure the sequence was counting correctly, but we can see again whenever the reset is triggered that it's working as we would expect. So with it high, it'll start counting. We have 0, 1, 0. It goes to 1, 1, 0. From 1, 1, 0, the next step would be 0, 0, 0. And whenever our reset falls off, it's going to reset everything back to the first instance in the assignment. And it will stay that way until the reset changes states. Not rising edge here. So from 0, 1, 0 to 1, 1, 0. All right, that should conclude it for this assignment. Thank you everyone for your time.